First, people invented programming, but then they realized that regular numbers just won't cut it, and they invented floating point numbers. But then someone asked, what about JavaScript? For JavaScript, this is not enough. And then they assembled again and invented NaN, not a number, so that JavaScript can be happy and can sing a Batman song. So yeah, na 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 Batman. But NaN exists not only to troll JavaScript programmers, it also exists to signify when something's not right. For example, you try to divide by 0, or maybe take a square root of a negative number. In this case, usually programming language will give you something that is none as defined by this standard. So keep this all in mind, and let's say we want to create a programming language, in particular a dynamic programming language, just like JavaScript. So here is an example of how you can organize object in such a programming language. So let's go through the code. At the very bottom, we have a main with sort of a test case where you create a bunch of values. One of them is a number, another one of them is a Boolean, some kind of a nil or none. We have a string, which is a pointer that we also turn into the same kind of value as anything else, because, you know, usually in dynamic languages, you have like a root object that kind of represents everything else in the system. And then we print them. Let's go up. Let's see what value is. And value, if you look at it, where is it? Here. This is a regular tagged union. It has a type as the very first field, and then it has a union that's, you know, either bool or a double or some kind of a pointer. And type is one of these. Type can be a nil, you know, like none in Python, nil in Ruby, this kind of stuff. A Boolean, a number, or an object. An object is basically a pointer that is here, that has a pointer to data and also has a type, which, you know, for example, string or array. I haven't implemented arrays, I just show string as an example. And then you have a helper for creating a string. All it does is just allocate some stuff, assigns it a tag, and duplicates a string, you know, perfectly safe. Perfectly safe usage of C standard library. I know, I'm a professional, trust me. Then we have some macro, you know, like X11 style, that let you create values. So for example, if you want to create a Boolean value, you just set a type tag, this one, to bool, and assign a union value of Boolean. Same with nil, you just set it as nil, then assign to, this is like an arbitrary because we're not going to be using the nil. The number, we just set number, and object, we just set it as a pointer directly. And a printer, this is kind of your usual dynamic dispatch. You accept a value, you switch on its type, and if it's nil, you print this, if it's Boolean, you print that, if it's number, you print that. If it's an object, you do another kind of a nested switch and say that if it's a string, blah, blah, blah. So nothing crazy. And if we compile it, so yeah, we will create a normal, it's called normal.c because it's kind of a normal way to implement it. And we run normal, we see that 314 for the number, we have true for our Boolean, we have nil for the nil value, we have Gundel the fool for the string. And then I also print size of values. This is actually going to be relevant soon. So size of one value is 16 bytes, so this struct. And 100 of these will be 1600 bytes. And don't worry if I went too fast through it. This is very basic. Just to TLDR, we have some kind of a struct that represents a dynamic object in our language, and we have like a bunch of helpers to create them and then to like unpack them to use them, right? And the main information here is that one of them is 16 bytes, which is, you know, a lot. And so what programming language creators decided that, hey, what if we can optimize it? Because a lot of these types, they don't need this much space. We can fit it into something much smaller. And if we can fit it into something much smaller, we can put more of them into a CPU cache line, thus making our languages much faster. And what can we use to do this? Well, the technique is called NaN Boxing. And what NaN Boxing means is that you take a NaN which is usually something that's rare and useless, and you try to pack this much information into NaN. So what was 16 bytes will only take 8 bytes because NaN is a 64-bit number. So how do we do this exactly? For all my basement dwellers, brace yourself because you're gonna be flashbanged in now. So let's look at NaN. Yes, so NaN is something like 0x7ff and then some magic number, so it's gonna be like 8 and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's convert it to double and we see that we indeed get NaN. So what we need to know about NaN is that in the beginning it's always either 7ff, you see if the sign bit is 0, or it can also be F. Yeah, it can also be FFF. So in this case, it's like a negative NaN, right? But we're gonna be using positive NaN with sign set to 0. Then this 7FF, you can treat it kind of as a magic payload, right? Like as something in the beginning of PNG, they also have like a magic number. You can treat it like this. I'm not gonna be talking about exponents, mantissa, blah, 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 all this nerd stuff. It's irrelevant here. And then we have this number, oops. Then we have this number, it's 8. And this can actually be any number except 0. So if we put 0 here, we get infinity. This is infinity in floating point number. And then anything from 1, you see like NaN, to, I guess, F, NaN. So this is this sector of bits. Anything other than 0 here will give you different kind of NaN. And in generally, NaN is kind of subdivided onto 2 categories. One of them is called quiet NaNs, and other are called signaling NaNs. So and signaling NaNs are usually used for like weird stuff like raising floating point unit exceptions and maybe debugging. So usually it is not advised to use those to pack additional information into them. And the way you distinguish signal NaN from quiet NaN is so by looking at the first most significant bit of this particular like I guess segment of a number. So if the most significant bit is 1, you have a quiet NaN. Quiet NaN is just for propagating through the system. So you can you can assume that the most places can use it safely. And if this is 0 and anything else is not 0, then you have a signaling NaN. So for example, if I put 1 here, you can see this is 0, this is 1, so this is going to be signaling NaN. If I put A here, you can see this is 1, and the rest doesn't matter. So this is going to be our quiet NaN that we can use. And the quiet part, the quiet place starts with 8. Everything from 8 to like F we can freely use. And as you can see, everything else, so from here to here is 48 bits of free real estate. We can pack here whatever we want. So the technique is using this part from 8 to F to store a type tag to know what is being stored, and then using this part as an actual payload, as an actual value. Yes, and so let's go back to the code and modify this file so it has exactly the same API, but different internal representation. First of all, we're going to need a NaN, which will act as a mask. So let's define it. I call it QNaN because, you know, quiet NaN, and it's going to be like 0x7ff. We said 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is our NaN. After that, we need to convert these type tags. Instead of enum, they're going to be like a separate number. So it's going to be nil, which we are going to use just actual this one. So it could be 0. Actually, let's like, it's going to be 1, 2, 3, 4, right? So I'll just gonna format them like this so you can see which sort of bit will go where, right? So it's just for alignment. It doesn't actually affect the code. Then we can define bool, which is going to be 0x1110001. And so when we OR QNAN and bool, this is going to become 9. So this is going to be 9. If we OR it with a boolean, after that we can take an object, which is going to be 2. And there's also number. Number, I'm going to special case it just to show how it's done. So you can totally box number into NaN, but then you lose some precision. You will only be able to store 48 bits. And why do you do that? Because, I mean, we're gonna be storing a number in a 64-bit number, but that doesn't make any sense. We will just store number directly. So we're gonna special case it. This is for an object type. We're gonna leave this. This we don't need anymore. Yeah, we're leaving this, create string, this helper will leave as is. And then instead of our values attack union, we're gonna have it as 64-bit integer. So it's gonna be type def unsigned long value. Yeah, and oh, unsigned long is 32-bit integer on Windows, so I'm gonna use long so Windows users can follow along. And man, this is like stupid. I'm not gonna type unsigned long. I just refused. Let's use uint 64t, and I guess I need to include std.h. Yeah, because I'm just not typing unsigned long. This is stupid. Yeah, we're gonna be storing this as a 64-bit integer, and this can be removed entirely. Now we need to modify these macros. So creating boolean is very easy. Let me actually remove that. And so how do we box a value into NaN? It's actually pretty easy. We take our NaN, so QNAN, we OR it with a tag. In this case, it's gonna be boolean, but since boolean is a regular number, by default, it's gonna be like an int, and we need to shift this number all the way here. So we shift it by how many bits? By 48 bits. We'll shift it to the left, so it gets into this position, and then we OR it with an actual value. And I guess we can go a little bit further, since boolean is kind of supposed to be either 0 or none, no matter what we get. We can do something like this, right? So if value 1, otherwise 0, yeah. So kind of do it like this. And I guess I need to cast it to integer, right? Yeah, just to be safe. So this is for boolean. Then to get a nil, it's even easier. So to get a nil, we just do QNAN. We OR it with nil, and that's it, because we don't store any other payload. We just left. So this effectively is going to be a NaN that is nil, right? This is our nil value. To store a number, what we are going to do, so what you can't do in C, at least, you can't just like, you can't just like cast value to double. Again, if you pass a double here as here, 314, and then you cast it to T, you will just lose this 0.14. So you can do that. You actually need something like C++, like reinterpret cast. When you first reinterpret it as a pointer to integer, and then dereference it into like an integer. As far as I know, this is undefined behavior in C, and since we're doing it in a macro, let's just straight up create a helper. We'll call this like number to value, and we just do it like this. And number to value is going to be this. It's gonna be returning value number to value, and it's gonna accept what? It's gonna accept double number. Yeah, you can, so if you pass an integer here, you can safely cast it to a double, so this should be fine. And yeah, so what are we gonna do here is we're gonna create a result that we return, and then we'll just straight up memcopy into result. We're gonna copy a number, and we're gonna copy double. So yeah, so we just grab all the bytes of this number and we straight up copy it into resulting value. So we're not losing any precision, we're not losing any bits. And we also need to do it the other way, so value to number later, and it's gonna accept value. So result is going to be, so our dynamic language only has doubles, only has floating point numbers, I guess, like JavaScript. So we are making JavaScript after all. It's gonna return double. We memcopy value to result, and then we return, and I guess I need to do size of value just in case. What is return result? Yikes. So next we need to handle our object, and the object is also easy, so it's a NaN that we XOR with an object shifted by 48 bits. And what we need to do is, I guess, just value that we cast as uint 64t. Yeah. So we just take a value and go there. I think my parentheses are in order. Yeah, and after that we need to print our values. Let's go one by one. First, we need to get the tag equals something, right? And tag is gonna be uint 64t, so 64-bit integer tag. And then we need to get some actual value, right? It's also gonna be something, some bit math. 64t, actually quite verbose as well. Yeah, so how are we going to do this? Let's open the calculator, which is, Python, and let's simulate some scenarios. So I guess let's imagine nil case. Let's grab this NaN. How do you do this? I guess you do it something like that, like hex. So to pack nil, we grab NaN and then nil tag, which is, right, so 0x0000 shifted by 48 bits, and we should be getting the same exact number, right? Which I guess is not super super interesting. So let's instead imagine that we have some kind of like an object, which I guess is 2. And right, and then the value is something like 1, 2, 3, 4, 5, 6. Yeah. So there is. Let's do something else. Let's do cafe babe. Yeah. So we can see this cafe babe here. This is going to be our boxed value. Should I need to make font bigger? Let me make font slightly bigger so it's definitely visible. Yeah, that's just like this. So how do we get back the tag? We need to get this 0002. The way you do this is you take this number and you need to mask it with something, and you mask it with NaN but in reverse, so inverted NaN. NaN, let me actually do qnan equals, like, actually use Python how it's supposed to be used, right? And now you get our value, and then with qnan but in, so inverted, and it should be ended, yeah, like this. And I need to hex it. Yeah, so you can see that I get rid of this magic number, like 7ff, and now I have 2, which is my tag for an object, and I have cafe babe in the payload. So in order to get just the tag, I need to take this stuff and bit shifted by 48 to the right. Oh, yes, it should of course be in like parentheses. And I get my 2, which is exactly my tag. Make sense? Makes sense. So let's write it. So our tag is going to be our value ended with QNAN like inverted and then shifted by 48-bit back. Then how do we get a value? So how out of this we get that? So we have our value and we also need to OR it. But this time, we need to end it. But this time we need to end it with inverted to this. So NaN and a tag. So I guess we do NaN, then we OR it with a tag, which is in our case the tag that we just got, right? So, and the tag that we just got is the tag that we kind of bit shifted by 48. And then we need to invert everything we got, right? So this is gonna be that part, then invert it. These are gonna be 0 and these are all gonna be 1s. What did I just do? I think I forgot a parenthesis here. Yeah, and we get back our Cafe Babe. So we get our payload back. So let's put it here. Again, it's value and inverted of QNAN sort with the tag that we just gotten. And then instead of switching on value type, because we don't have it anymore, we switch on the tag. And then it's the same thing. So if nil, we print nil. If Boolean, we do actual value instead of value that as. We print this, and in case of number, actually number is a special case, so let's remove it from here, and we are gonna handle it right there. So how do we handle a number? Well, we just check if QNAN and our value and ended together are not equal to none, right? Because so if you imagine like a hex where you end none with literally anything, right? So regular number, you will always get 0. Not 0, you can get something else, but you will never get none. That's the point. So you compare it to our NaN. And in this case, we will just do, I guess, just printf number, right? We'll print in a big float, so like this. /end and our value. Value to number, as a matter of fact. So this should work. After that, an object should be the same thing, but here we switch on type, but we need to get an object. So object, and I guess it's gonna be a pointer equals to, so actual value that we got on is gonna be a pointer. So we need to reinterpret it as a uint ptr t, like this, and then you cast it again as an object pointer. I'm gonna have so many compile errors. I'm already kind of expecting them. So let's try to compile it. Yeah, and ooh. So what do we have here? Implicit declaration function print. Where do I, yeah. So this has to be a printf. That's the first one. Anything else we have here? Value as object data. So I forgot. Yeah. So it's just object data this time. What else? Left shift count more than equal than width of type overflow for what? Bool. So it's here. Oh, it probably wants me to cast those to 64-bit integers, right? I'm pretty sure like that's the case. So let's just do this, and that. This should work. And anything else? I don't think so. Let's just compile it again, and it worked. And if I run it, normal, terminated by segfault. Uh-oh. Uh-oh. So what do we have here? All right, I I supposed to shift this back, yeah. Because I got the tag, so I can compare them with these numbers, and yeah, so I need to shift it back by 48 to get an actual value. Let me compile it again, and this time we have, yeah, we have true. Why do we have true 2 times? Oh, right. This is supposed to be an early return here. Yeah, I'm sorry. This is actually like 2 a.m. Yeah, and now we have our pi, true, nil, candle of the fool. And look at this. This is 8 bytes. And we saved half of what we saved. As you can see, it's pretty easy. There's a little bit of bit magic overhead. You can get rid of this shifting by 48 back and forth if you shift them here when you define them and add another mask that you just order to make this 0, but I guess this was just easier for me to write. Also, what I should point out is that sometimes you can see that people box objects not by using a separate tag here, but they actually use a sign bit. So if we go back to the browser here, they would set this bit to 1, and then they instantly know that whatever here is a pointer, just to, I guess, separate values from a pointer. And also doing it like this frees up another tag for you to use for something else. And another point that maybe people who are familiar with floating point numbers can point out is that what if your language actually has NaN? So how do you distinguish an actual NaN that you might want to return from boxed NaN? And to do this, people just take one of the NaN values, they call it canonical, and then they treat it as an actual NaN. As a matter of fact, if we go to GitHub, like here, this is an issue tracker of WebAssembly standard. And a person here asks what the motivation for NaN canonicalization. And he points out that in ECMAScript code, all NaN values are indistinguishable from each other, right? And oh, why WebAssembly is different? And the answer is because, well, WASM wants to support NaN Boxing. WASM wants to be friendly to NaN Boxing, so people in their implementation can use this optimization. So yes, this technique is actually super common and super useful. On top of that, there is a book that's called Crafting Interpreters, a very good book about, well, crafting an interpreter, and it has a chapter on optimizations, and one of them is NaN Boxing, and they also go quite in depth about it. I will leave all the links in the description so you can check this out. And one last thing I want you to recommend, not about NaN Boxing in particular, but just about bit packing stuff, is this amazing talk by Andrew Rees from Better Software Conference. And I kid you not, it's almost 3 hours long, but it's super technical and it's packed with some absolutely crazy amount of bit packing techniques and just incredible stuff. I really recommend you to watch this. I understand you might not have 3 hours of your time, but just please, just slowly devour it as some kind of a TV show. Instead of watching some Pluribus or some other Netflix slop, just watch this. Your brain will expand and you will have 5000 IQ, I guarantee you. I'll also put this link into description. And yeah, that's it. I hope this video was interesting. Sorry, I was kind of out and about, couldn't make any videos sooner, but more will be coming. So like, subscribe, all this usual YouTube stuff, and I'll see you next time. Bye bye.